me to share little my thoughts over here. I could not take time because the time is already over. I have already closed, 6 minutes from the beneficial time of one particular speaker. Therefore, going to finish it out over here and wish a grand success again for this webinar. Thank you all very much. Jai Hind.
Thank you, sir. The words were very much inspiring for the mathematics department of NIT Agartala, and we will surely strive harder to make it a success again. And now I would surely say that the sir's words about mathematical modeling gave us an understanding about it and how to use it in the real field and how to save any future pandemic, as we are in this pandemic, which is killing many of us and getting many of us infected. So this mathematical model will surely help us in saving lives, and this is one of the key importance which is surely straight from the sir's speech. So thank you, sir. Now it's time. It gives me immense pleasure inviting one of the most elegant researcher, Professor Oscar Castillo from Tijuana Institute of Technology, Mexico. Professor Castillo received the Doctorate of Science degree in Computer Science from the Polish Academy of Science, Warsaw, Poland, and is currently working in the Computer Science Department of Tijuana Institute of Technology. His research interests include type 2 fuzzy logic, fuzzy control, and neurofuzzy and genetic fuzzy hybrid approaches. He has published more than 90 journal papers, 5 authored books, 20 edited books, and 200 papers in the conference proceedings. Professor Castillo is the Vice President of the Hispanic American Fuzzy System Association and the past President of IFSA, the International Fuzzy System Association. Welcome, sir. Today, he will be presenting a session on neural networks, fuzzy logic, and fractal theory for COVID-19 modeling. Over to you, sir.
Thank you for the nice introduction. Let me share my I will share my slides. Can you see the slides?
Yes, sir.
Okay. So I can start then. Okay, thank you very much. I'm very pleased to be talking to you today, and I was supposed to be in Agartala in March for the conference, but I couldn't come to your place because of the pandemic. So I owe you this presentation. Sorry. Okay. So I will talk today about sorry. I will talk today about my work with some of my colleagues with using some computational intelligence techniques for solving COVID-19 problems. So let me show you. So this is a summary of my presentation, sorry, of my achievements. And this have been mentioned before. So this is my group in Tijuana Institute of Technology.
You can make the full screen.
Let me try. It's okay?
Yeah.
Okay. So I will basically I will talk about 5 applications. The first 3 are applications from combining fuzzy logic with fractal theory or neural networks. Then at the end, I will show 2 applications that I work with 2 of my colleagues in Delhi, with Professor Deepak Gupta from Delhi. I have solved 2 problems also with them. So 3 are from my group in Tijuana and 2 from my collaboration with the professor from Delhi in India. So for the first one, this is a. So is there a question? Okay, so this is the first application. Is a combination of fuzzy logic with fractal theory for determining the future values of the COVID-19 time series. So basically, the idea came from my previous work on fractal dimension application for classifying bacteria. This was more than 25 years ago, but I had worked on that before, so I had some previous work on that, and I came with the idea of trying to apply these concepts in this kind of problem at this moment. And basically, what we did at that time was that we needed to classify bacteria in a production process, food production process, and we applied at that time the concept of the fractal dimension to characterize and then classify which bacteria were present in samples of food in the production. So that was a real problem, and we used the fractal dimension to measure the complexity of the colony of bacteria in that case. And then later we came up with the idea to apply this concept in time series prediction, but at that time was for economics or financial time series prediction. And that work was the motivation for applying it at this moment for this particular problem of the COVID-19 time series. But let me show you very quickly which are the basic concepts that are needed in this case to do this application. Basically, we can build a fuzzy rules, a fuzzy set of rules based on the values of the fractal dimension in such a way that we have a classification scheme for classifying the objects that we have in particular in any application. And in original case, we did it for the bacteria to classify the bacteria, but we can classify other things, of course. And in a specific case of time series, what we have is a set of data, and we can cluster the data, and then we can build rules for groups of data, and these rules can be used to forecast with similar data in the future what will happen based on this concept. So in this point, we also came up with the idea that basically the fractal dimension was given as a number, but this number was not a precise one because we obtained those values from samples. For example, in the case of bacteria, were samples of food, and other problems are samples of other things like sound or other concepts. And so these samples can give you an estimation of the fractal dimension. So basically, the fractal dimension can be also viewed as a fuzzy concept. So basically, we define fuzzy fractal dimension to convey or to capture the uncertainty on calculating or estimating the fractal dimension. But very quickly, just to remind you of the concept, one of the ways to calculate the fractal dimension is the simplest one is based on this equation 1, in which we try to cover a geometrical object with a number of boxes, and we change the size of the box. And in the limit, this will give you an approximation to the fractal dimension. Basically here, so the number of boxes covering the object is n, and r is the size of the box. And this gives us the box counting algorithm, in which basically we can implement this idea, counting the number of boxes for different sizes of r, and we can approximate the dimension d with many of these values of r that will give us different counts of boxes covering an object. So basically, it's like in this figure, in the plane, the example here, so this particular curve C, we need these boxes to cover it for a particular size of r. And if we change the size of r, we will need, if we, for example, reduce the size of r, we will need more boxes to cover it, or if we increase the size of r, we will need less boxes to cover it. But these give you an idea of the complexity or complicated form that the curve has. So if the curve is more complicated, you need more boxes, and if the curve is a simple line, then you need less boxes. Basically, if you have a line, then the dimension is 1, and if you have a curve so complex that you cover the whole area in the plane, then you have dimension 2. But this definition will give you a value between 1 and 2 when you are on the plane for different complex objects that you can have in the plane. So the idea is that you can differentiate different complexities of the forms of the objects on the plane or in other three-dimensional or other scenarios also, but here is just to illustrate on the plane. And in this way, we can use a regression to estimate the dimension D as the plot in a plot, a logarithmic plot. So D is like an estimation in equation 2 of the dimension, like in this figure is shown. So basically, is the slope of this line, and the points are around this line. So this is the regression, and so this is a linear estimation of the fractal dimension, in this case by the box counting algorithm. But of course, this has some uncertainty when we do this process, and that's why we can use these values in a fuzzy way also. Anyway, so this is the way that we can use very easily, we can obtain very easily a value of the fractal dimension as an estimation of the fractal dimension. And then we can, if we have data for any problem, we can try to use this concept in the following form. We can cluster data from geometrical objects from this data, from basically the clusters, and then we can formulate our fuzzy rules based on the clusters to determine or classify which objects we have in that case. So in this form, we can view it as a recognition, object recognition, or object classification, but also it can be used for time series prediction, and if we view the prediction as an object, is the same thing. So anyway, around the year 2001, we applied that to predict the exchange rates of the US dollar against the Mexican peso, our currency, and we did that in about 2001, around that year, and we found out that this was very good in prediction of that time series at that time. So this is an example of a time series. So basically, you can cluster the different regions of this time series, and then you can have rules for the different behaviors of different regions of the time series, and you can predict in the future how these cyclic or erratic behaviors can happen in this time series. So that's the process. And basically, we can, this is an interesting thing from the point of view of the fuzzy logic, because based on this definition, we have uncertainty, and we can define a fuzzy fractal dimension. We did it with intuitionistic fuzzy logic at one point, and also with type 2 fuzzy logic. In any case, it's fuzzy logic, so it's fuzzy fractal dimension. For example, if we do it with intuitionistic approach, we can define, for example, with a particular form of membership function, like in that case, it's the generalized Bell membership function, and we have a membership and a non-membership function in this case, because it's intuitionistic. Or in the case of type 2, it can be a membership function with the secondary membership function to represent the uncertainty over defining the values of the memberships of the primary membership function. So it's the same idea, but with different approach. You can do it in any way. And of course, depending on the problem, can be better with one approach than the other. So basically, this is the idea of this definition. I will not go into so many mathematical details because I want to show you applications, but you can construct many things with this concept and generalize the whole theory of fractal theory with the, coming from the fuzzy point of view, depending on intuitionistic fuzzy or type 2 fuzzy. So let me show you a particular case, I think more easy to understand. Let me show you, for example, this is for prediction. Just I forgot to show this before. the example. So if the fractal dimension is a particular value and we are at a certain point in time in the time series, then we can find the prediction based on these two inputs, viewing the fractal dimension as a fuzzy variable. In this case, we give fuzzy sets or linguistic values to the dimension. We can view the dimension as low, medium, or high in this way. Instead of using directly the numerical values, we fuzzify the dimension in this process. So we will have the objects, we find the clusters, then we post the rules, and it can also be Sugeno fuzzy rules. The same idea, just in the outputs will be equations. In this case, for example, we can use AMPHIS or some method using neural networks or genetic algorithms to find the parameters in the outputs of the Sugeno fuzzy rules. So another application we did about the year 2006, we published that in Information Science Journal, was this, to show you the versatility of the concept. We had a problem in manufacturing sound speakers, a real problem in a plant in Tijuana, Mexico. And what they did at that moment, they were testing a sample of the speakers that they were producing manually. So they hear the sound, and a person, an expert, was telling that if the sound of the speakers was good or not. So they wanted to automate this process, and basically what we proposed, and we solved the problem in that way, we use the sound, the signal of the sound used through the speaker to determine if the speaker was good or not. For example, a particular sound using the speaker, if the speaker was good quality, was like in this figure. But if the speaker had a particular defect or problem, then it was very different. Like in this one, is very, very easy to see visually. That is very different from a good speaker, a good signal. So basically, but this is one example. There are many possible defects, and also we want to automate. So what we posed was a set of fuzzy rules based on the fractal dimension, because of course, I told you before, the fractal dimension of this figure is closer to 2 than in this. So this is closer, it's lower, a lower value, closer to 1, and this is closer to 2. So basically, very different values. But of course, it's not only that, it's also depending on the difference between the two signals. So the difference is value, like an error. If it's a small, regular, or medium, and the fractal dimension is small, etc., then we can state the fuzzy rules to determine the quality. The quality is excellent if the difference between the signals, the signal of a particular sound from a speaker is very close to the ideal one. The difference is small, and the fractal dimension is small in the sense of this case, then the quality is excellent, and so on. And if the difference is large and the fractal dimension is high, then the quality is bad, and we can state the rules. And this was the problem here is not just the rules. In this case, also the membership functions. So they were calibrated so that the results were very good, and we were able to validate with real values that it was giving the quality in a good way, as an expert will do. So this is just another example, even if this is not COVID, it's just to show you very easily that this is applicable in a very easy way. It was published, like I told you, about 15 years ago. Now coming to the real application now at this time of forecasting COVID-19. And basically, we have been given these problems in our institutes to solve. This is, of course, very important for our country around the world also. So they told us, okay, we want to forecast, try to use your methods, and we did try our method, this method I have explained, combining fractal dimension and fuzzy logic, basically. So the same idea, just in this case, we use that data sets from 10 countries in the world to test that it was working well. We use windows of 10 and 30 days to see if short term and longer term we can predict still with good accuracy. And we will see in a few moments that the accuracy is over 98% on average. In some cases better, in some cases lower, but 98% is very good, I think, for us. And so basically the proposal is like this. In this figure, you can see we have the time series as input of confirmed cases and dead cases. They enter the fractal dimension module. Basically, there the box counting algorithm is used to calculate or to estimate the fractal dimensions of the dead and the confirmed cases. Here we use nonlinear and linear approximations to have more information, not just the way that I showed you before, but it's similar. So these 4 inputs enter a fuzzy system that we devise the rules, the fuzzy rules, in a fuzzy way with small or large values of the dimension and so on. Then what we will predict in those cases for confirmed and dead cases. And basically the fuzzy system gives an increment, even positive or negative, when of course the cases are increasing, always positive delta p, but sometime in some time series eventually they decrease, so delta p can be negative also. But in any case, it's an increment, and this is added to the previous values and to determine the future values. So this is just the idea. So the fuzzy system is like this. This is just type 1 at the moment. So we try the easiest thing. We can do also type 2 to improve even more, and maybe longer time windows in the future will require type 2 because there is more uncertainty in predicting more into the future, or with more data sets of bigger size, or other problems also. Anyway, this is the structure. These are the rules, very easy. We developed 6 rules to determine the increments depending on the values of the fractal dimension. Basically, with our knowledge, like I told you before, of if this low is less complex, if it's high is more complex. And basically, we, for example, this is the plot of the dead cases of China for that period. This is not this moment. It was around, I published this around May. So this is from April to, no, from March to April, something like that. I mean, the data. And these are the fractal dimensions calculated for the 10 countries that we use: Belgium, China, France, Germany, Ireland, Italy, Spain, Turkey, UK, and US. And you can see there the differences. Of course, countries that were having more problems had higher dimensions, like US has even a 1.8 here. And more stable countries had lower values. So this is just very, like very easy to see, but of course, different values determine different stages of the pandemic or the COVID problem in each country, of course. But this is just an idea for that period. Of course, if you do the same thing at this time now, the values change because the time series is now in a different stage. So this is not fixed. This has to be recalculated every time because it's changing a little bit, maybe in few days, but if months, then these values change. But this is just to show. So this is just in the prediction, for example, for Belgium, for 30 days, very, very good. Then for Spain and for Mexico was super for us, the prediction, and just some of them. So this was our original paper that was published in a Journal of Chaos, Solitons, and Fractals around May. Was our first paper in a journal of COVID-19 application. Then we also tried to study the spatial problem. This was temporal, predicting in the future, but then also the spreading process is spatial, not only temporal. So we also wanted to study the process of spreading in space. So for that, we changed our tools. We use self-organizing maps, which is a kind of a neural network that you may have seen in your literature or in your studies for the students. And basically, this kind of neural network is a clustering neural network in which you give data, and this kind of self-organizing maps the other name that they have this kind of neural networks, try to organize the data in groups by themselves. So you don't teach the neural network. It's like a organization. So we applied this to several countries again of the world to see how this was spreading. And basically this, very quickly, because I don't have too much time, you can research this. These self-organizing maps proposed by Kohonen basically have only two layers, input layer and output layer, and the input layer is the data, and in the output layer, these data are grouped in some way. And this is unsupervised because it's not teach. So it's like this, and you have a group of data which are the x1 to xn being grouped in some way, here shown with colors, because basically we did this coloring for the country and for the world, because green is for usually used for when the problem is not bad, and red is for when there are too many cases or many deaths in particular region. So these are the equations, very basic equations. So this is very simple neural network. Just using the distances, they produce weights for the connections, so that the groups are formed in this way. And the data, here is the web page of the data is for the humanitarian data exchange, basically from January to May, to see what was happening at that time. And this was the approach. You can see country 1 to country N entering as data, and they are grouped. We put colors to the groups. So basically, for example, you can find countries with, this was a very beginning with only problem was in China, Iraq, and some countries in Europe. All the rest of the world, we were happy, we had no problem at that initially at that point. Then later this was spreading throughout the world. But the beginning was only China, mainly Chinese in red, and then Iran, Italy, and some countries like Spain, France, but other parts were in green mostly. And this was our country, Mexico. Later, also the states, we clustered the problems. We are in my city, we are in this part near the US in this point. Mexico City is in this part. So Mexico City was the biggest problem. They were red almost all the time since the beginning. And we were orange. Now I think we are yellow the last week. Anyway, so basically that's the idea. So we clustered. This paper is also in Chaos, Solitons, and Fractals journal. And they are open access because all COVID publications are open access. So you can check the complete papers. You can download from the journal, because they want this to be available so that everyone can replicate or try to replicate this. So this basically, this method has been applied to many countries now, and they have referenced our work because we were the first ones to do this. Now they have applied this to Brazil or other countries. I'm not sure if they have applied it to India, so I think you can do it. I haven't seen it, so you can check. So it will be interesting to also apply it here, and you can publish a paper on COVID-19 also in this way, but not also for publishing. Of course, important to solve the problem. Anyway, so here is the more recent problem now. Now, US has more problem. China is out of the problem almost, and India is in some problem, but I think this is not the new one. But Mexico is also yellow at this moment, and Brazil is in some problem, and Russia also. Anyway, so this is also in time. So we want to connect. This is our goal now. Connect both things. Connect. This is a spatial analysis, but also is evolving in time. So it will be like combining the spatial, because it's like picture for different times, but it also with the time process will be more interesting. Anyway, we also, let me show you this. We also, in the case of Mexico, we correlated the cases with some other illness, for example, hypertension and diabetes. They have been found that persons with these problems, they can be more possible cases of COVID. So we found out that the map of the diabetes cases and the hypertension cases were related to the map of the COVID-19 cases, and this was done with these cojones maps, basically. And so, but we did not do this for the world because we could not find all the data for doing that, but this is also still thing that can be done. And in summary, you can make many analyses. This is just an illustration very quickly of different things to give you ideas so that you can research this, or you can maybe do even better things than this, but to show you what we have been able to do with these methods, and not only to publish, but also to solve problems. And of course, this is important because if you publish, as this is available immediately, open access, and they are publishing very quickly these papers because of the necessity of solving this problem. So other people are trying the same things or different things or better things that everybody's is publishing to solve the problem even in a better way. Anyway, let me show you another approach. This is an ensemble of neural networks here using type 2. As you know, maybe you know me more for type 2 fuzzy, but here solving problems, you have to apply whatever is needed to solve the problem. So whatever is easiest and quickest to solve the problem has to be applied, even if I like more type 2. But in this case, I managed to put some type 2 in this paper in collaboration with my people in Tijuana. So what they try is another approach to predict more difficult cases or difficult countries. And basically, they consider, in this case, more countries, 26 countries in the world. And what they propose is that we can use ensemble of neural networks, meaning that you use many simple neural networks. For example, you can use a simple neural network for each country or regions of the country, and then you can combine the outputs of each of the networks to improve results. So basically here, the type 2 fuzzy system at the end improves the predictions of the neural networks based on the combined information of all the neural networks. So it's like a fuzzy system in which you input the outputs of the neural networks so that the type 2 fuzzy system revises the predictions to improve them in a better way. And also, we applied a Firefly optimization algorithm to reduce the architecture, to optimize all of the architecture of this hybrid system, which because it's many neural networks with a fuzzy system of the output, so it can be very complex. So it was optimized with a Firefly algorithm also to have a better result. So this is the situation. You have many neural networks, neural network number 1, number 2, and so on, and giving a prediction each of them. Then these are the inputs to the fuzzy system, then final prediction. Okay? So basically, the type 2 fuzzy system is like this. The errors of the neural networks are the inputs, so that the weights assigned to the different predictions are evaluated based on the errors, because a neural network that is very good, the error is very low, then the weight should be higher to that network because it's giving a better result. And so it's like someone expressing, if these were persons, a better expert will be given more weight to the opinion of that expert, and so on. And higher errors will mean lower weights because those networks were not so good. Anyway, this kind of fuzzy rules based on the errors, in this case, of course, falsified, small errors, higher errors, and so on. Then the weights are assigned, and these weights will help us aggregate or integrate all the predictions to improve the predictions. in this way. And basically, this aggregation is very simple aggregation in this case, based on the weights. And so this is just the optimization algorithm. I think I will not deviate much from my talk explaining the algorithm, but if you know genetic algorithms, particle sum algorithms, this kind of algorithms are basically to optimize fuzzy systems or any system and using a population of solutions, and basically a population of this kind of architectures were being evolved until the optimal one was found, and then that one was used to really obtain the results. Basically, that's the idea. So this is the data set, just here concentrating all the countries, 26 countries that I consider here in one plot. Dead cases, that was for the confirmed cases. This is for the dead cases. Here you can see very high for the US. And I will tell you a small joke. They say this because Mexico is the guilty one. We are always the guilty one for the problems of the US. It's just a small joke, sorry. Anyway, so the experimental results, we tried these predictions also here to optimize the generalization capability of the neural networks. We tried different percentages of training data and testing data. So the less possible so that the generalization was better. So averages of 3 runs for each country are shown also to do a statistical test. And here, for example, this is for one particular ensemble for China. You can see here with 3 modules kind of errors that we have. So they are very good with different integration methods, so using type 2 or just an average, simple average, not so much difference. In this case, with a case that is very stable or simple, there is not much difference. Complicated cases will require better aggregation, of course. This is China for prediction with this model. In the top are the 3 modules, the 3 simple neural networks, and then the image below is the aggregation of these 3 shown here are aggregated with one final output. Here is the convergence to the error after the iterations of the learning of the neural networks. And here are the comparison of the different methods of aggregating the results of the 3 neural networks. Type 2 is the blue one, which is here not the real data is this green here. So at the beginning it's good, but then they are some distance apart. So of course, every predictor is like that. If you go very many periods ahead, then they lose capabilities. So this is difficult, of course, for any system. This is also with other experiments. This is for more modules for neural networks being combined. You can reduce the error to the 10 of them to the 9 here, but you can see aggregating the errors are a little higher when you aggregate. These are on the order of -6, and here are -9, because good aggregation will reduce the error even more. These are the kind of fuzzy system use, type 2 fuzzy systems. And predicting more ahead, here the type 2, this last type 2 model is better because this is closer to the, in that cases, to the real one, which is the solid black line. Here is just a summary of all the countries. Here you can see that you have a good challenge. I mean, the highest error we had for the 26 countries is for your country, for India. You see, almost in all countries, we can have very low errors in prediction, but India is the one that at that moment is giving, we made this paper was giving us the higher errors. Not too big errors, but higher errors. So I think you have something more complex here, or maybe the data, we need to use more data, or the data has some errors. I'm not sure what is happening, but higher errors there. So this is just a summary of this. Let me show you different thing. This is from my collaboration with Professor Deepak Gupta from India in Delhi, in difficult name of the university. I cannot recall now, but he's trying to do different thing, not prediction. He says here prediction, but it's really diagnosis, because they are using the X-rays of persons to try to say if they have or they don't have this COVID-19. So basically, they use convolutional neural networks, two types of convolutional neural networks, and simple decision tree model to compare. And also they compared with regression models. And in this case, what we have is this kind of situation. These BGG16 and Inception B2 are convolutional models, two different convolutional neural network models. And this is just a decision tree. These are the data from X-rays and CT scans from images, real images. Feature maps are extracted, and then they are input into these three models. Then you have the results so that you can discriminate normal case, pneumonia case, or COVID-19 case. These are easy. Basically, at the beginning, even medical doctors were confusing the usual pneumonia, but even bacterial pneumonia, with COVID-19. So now it's very important that this is very easy to distinguish, because it's different. The medicine or the treatment is different. So these are the kind of, this is open access. You can check these data sets. There are many data sets now also being given real data daily. So you can, this is one of the data sets that you can check from in this case, this X-rays and CT scan images. So basically, these regions, these wide regions, depending on how big they are in how they are, they give you the information to say if you have COVID-19 or not. So they train the systems. Basically, this is the training of the neural networks according to number of epochs. These were for normal cases, for pneumonia cases. And at the end, you can see the results. I'm skipping many slides. This paper is also online now to be published in Soft Computing Journal. And you can see here that we have very good precision and recall. Also, this is for COVID-19, but not so good for normal pneumonia cases, but this is as best result that you can find now in the literature. And of course, there are bigger data sets. We still have to test other data sets. This is just one of them, and there are many in the world for this problem. And of course, there can be difference from country to country. Maybe I'm not sure about that. I'm not an expert on medicine, but this is very, very exciting results. And basically, this is the idea here to make an early diagnosis, not forecast. This is not so good a word, but the physicians, I mean, the medical doctors, they don't like the word forecast when you are saying it's kind of like a forecast, because you are predicting if the person will be ill in the future in some way, but they don't like the word. But anyway, this is like very early with these images, say if the person has or not the problem, because the problem is that you need to distinguish quickly to know if the patient is probably with COVID-19. So anyway, this is another problem. And also with them, with Deepak Gupta and from Delhi, they try to apply differently than ours adaptive neurophagy inference system, which is called AMPHIS. to predict COVID-19 in India. So they have this paper also submitted to Applies of Computing, and they have the data of all the states or countries, regions in India, to predict regions, like in my case, Mexico, the states, and they use AMPIs, and like this, they have the COVID-19 data for India in the national data in also in the cloud, and also they have local data from regions, and they combine this information to form a data set. They input that to AMPIs, and then they make the prediction. And this is the kind of flow process that they have. Basically, this is the process of the AMPIs. The data comes, and there is a clustering, and then they find the parameters of the membership function, the update parameters, and so on. And this is the optimization with a pollination algorithm of this system. This is the structure of AMPIs. If you know, the model is very well known to you. Basically, a fuzzy system is embedded in a neural network so that the learning of the neural network is used to find the parameters of the fuzzy system. And they have this kind of data sample. I took some of the plots of our paper just to show. This is for January to June data in India of confirmed cases. This is the prediction they did for until August, and this is very, very, very good. And this is the kind of error they have to the 10 to the -3. They can improve the error, but this is good error still, because as you recall, for me, predicting India was difficult in my method. So you should try other methods, of course, like in this case. And anyway, this is also only 86% accuracy. So it's good, but it can be improved. But this is the thing that they have at the moment. So just a conclusion, I try to show you different kinds of applications of different methods from computational intelligence. I show you from fuzzy logic, type 1, type 2. I show you from neural networks, self-organizing classical neural networks also, and also fuzzy logic, which is mainly, fuzzy, fractal dimension, which is basically from mathematics, but combined with fuzzy is I believe it can be considered also intelligent technique, but this is another discussion. So anyway, I think you can do many things. I think this is something that you can use for your work. You can try to apply this similar problems in your case in India or in the world. There are other things there are other problems also in related to this thing. Also, there are people trying to predict problems in economics based on the COVID-19 data. So this is different because, of course, COVID-19 has affected the economy of the countries in unemployment, exchange rates, and so on. So there are also people working on that in relation of economics and finance with the COVID-19 and many things. So I think this is it for me, and I hope I have been able to motivate you to do this applications. And if you have questions, I think I have some minutes for questions. Thank you.
Thank you, sir. A great session which really gave us an insight of your relevance in the field. So now we will have a short 10 minutes question session, which I particularly find it as the learning session. So everyone is invited for the question. You can drop it in the chat box or you can ask to sir directly.
You know, my inspiration is Professor Sade. Of course, he's the father of fuzzy logic. He died at 96 years. He's still doing research, and but he also always told us I was present in about 20 times in his conferences and his keynotes in conferences. And he also always told us, don't hesitate to disagree with me. He told us that because he wanted people to ask him or to say if they were not agreeing with him in something or another. And hopefully I can have some input from you. I have seen some questions there. Can you read the questions?
Yes. Yes, sir. Sure, sir.
Please.
So we have a question from Yakshit Agarwal. Can we tackle COVID-19 with quantum computing?
I guess, well, there are many points, many parts for that question. Of course, quantum computing in general could help us process more data. From the beginning, I believe the Chinese are doing that, of course, because they have more of these quantum computers in China than in other places in the world. So they should be, I'm not sure, but they should be using them because you can process more data, and we are restricted because of our computers to use smaller samples data of the data that is available, because right now it's a lot of data available because they are daily uploading data to many databases, and you can try to analyze many of these. And so in that sense, if you could use these kind of computers, but also the other side, I don't know if the question was from that side or from the side of, because there are algorithms based on quantum computing that are also, even if we process them in our simple PCs, they are giving better results. And for example, in optimization, there are, for example, a GA process with quantum algorithm maybe can give you in lowest number, in a lower number of iterations, a better result. So in that sense, can also be helpful even if we don't have these quantum computers because they are too expensive. We can use quantum algorithms or quantum optimization algorithms simulated in a PC, and maybe good results, better results can be obtained. So I hope I answered this question in the way that it was intended.
Okay, sir. We have a thumbs up from Yakshit Agarwal. Thank you, sir. Now we have the next question by Mr. Shankar Swarup Das. He asks us that how can the fuzzy analysis help to predict COVID-19 situation for next 2 years?
Yeah. You know, fuzzy model can be as complex as you can imagine. I have, for simplicity, consider the simplest way, and I have avoided something that may be very interesting for you. I realize now that because coming from, I have also colleagues in other countries, in Turkey, in Morocco, and other places where they have been using fuzzy differential equations to model COVID-19, and this maybe will be better for trying to see the behavior in long run, more time, because these models, like I have shown, are better to say next week, even maybe 1 month, 2 months. I'm not sure, but if you want to study the problem more like a epidemic model, things like that, then maybe a kind of differential equation model is better. But it can also be fuzzy because of the uncertainty. You can use fuzzy differential equation, even fuzzy fractional differential equation, because of you want to consider memory in time in the model, then fractional derivatives are better. So you can use fuzzy fractional then type 2 fractional differential equations for modeling this, and it will be very interesting. They are finding very interesting results. I have colleagues, and I also publish papers with them in this regard. I'm mainly advising them because in my group I don't have mathematicians. I have that disadvantage. So, but these friends of mine are mathematicians, but they need to understand how they can apply it. So in some way I can make them make these theoretical things come to real situation. But this is another way, I think, to consider long run.
Thank you, sir. Sir, the next question is from Shaptadut Bishwas. He asks that how can we improve global market system with the help of fuzzy logic system?
Global market?
Global market system.
But I didn't understand if it's related to COVID-19 or not. It's in general or...
Sir, I think he's putting it out of the context. He's just arguing about as a whole, the global market system. With the help of fuzzy logic system, how can we improve?
Yeah. Well, in general, of course, you can relate to, like in this case, of course, you need prediction in that case, but if you want to consider the macroeconomic view, it will be similar to their case. Macroeconomic view will need differential equations also, because the competition between countries is similar to Lotka-Volterra models, and so not exactly, but similar. You have differential equations and you have variables, macroeconomic variables from the countries. And this can also be fuzzy, because fuzzy differential equations will be a better approximation, I think, than using only numeric differential equations. And I think this will be a way. If you consider actions, a certain time, actions can be done easier with fuzzy systems, like I have shown here, because the decision making in a point of time from an agent taking a decision, you can have a fuzzy system, fuzzy rules to decide. But if you want to view the dynamics of the global market, then fuzzy differential equation approach will be better.
Okay, so today we have our last question by Mr. Abu. We have the last question now. Now he asks us that is there any mathematical modeling technique that could be used to predict the COVID spread? Or generally, if we ask, is there any mathematical model which could be surely used to predict any pandemic spread?
Yeah, I think it can be generalized because they have some similarities. All pandemics will have some similarity, and I think you could try to extrapolate, for example, from what happened with SARS or other pandemics that were occurred before. And I think that this, because actually what we do as humans, as human experts, like we find similar things that we modeled before, and we make our models in some way similar to other models that we did. So we could try to do that. We could try to use that to make these more general models, and like these ones will be like special cases of the other more general models. I believe that I haven't had time to think about that, but it's possible also.
Thank you, sir. Here we come to the end of our question session. Now,
Okay.
I would like to invite Dr. Pinky Majumdar, Organizing Secretary of our international webinar, for the vote of thanks. Over to you, ma'am.
Am I audible, sir?
Yes.
Am I audible, sir?
Yes.
Am I audible? Respected Keynote speaker, Professor Oscar Castillo, sir, Tijuana Institute of Technology, Mexico. Respected resource person, Professor Bishwajit Sarkar, Professor Odrijit Goswami, Professor Monoranjan Maiti, Professor Nita Shah, Professor Ranjit Kumar Upadhyay, and Professor C.K. Jagi. Respected Professor H.K. Sharma, sir, Director NIT Agartala. Respected HOD Mathematics, Dr. Baby Bhattacharya, Madam, and other faculty members and all participants. Today, on behalf of organizing committee, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this international webinar on mathematical modeling in the context of COVID-19 and the global crises, organized by Department of Mathematics and IEEE Student Branch of NIT Agartala. At that outset, I would like to thank our keynote speaker, Professor Oscar Castillo, Tijuana Institute of Technology, Mexico, and other resource person of this international webinar. Sir, we are really enlightened with your kind presence. I would like to thank our chief patron of this international webinar, Professor H.K. Sharma, sir, Director NIT Agartala, for his enthusiastic support. A special thanks to the patron of the international webinar, Dr. Baby Bhattacharya ma'am, HOD Mathematics, for her unflinching support. I would like to thank all faculty members, especially Dr. Mantu Das and technical staff of Mathematics Department for their active coordination. Our heartfelt thanks to our students and all participants of this international webinar. With these warm words, I move to the end of today's technical session 1. Our next technical session will be started today from 3 p.m. I request everyone to be present in the Google Meet, which will be starting from 3:45 p.m. Just exactly 3 p.m. we will start our technical session 2. Thank you, sir.
Thank you. Bye.
Thank you, sir.